change my background as well. Yeah, that is cool.
Perfect. So I think I've started the streaming. Just give me a few seconds more.
Yep. So are we live?
Just a few seconds. I'm just waiting. Yeah, perfect. It's done. Awesome. So hi Tejaswa, welcome. And I'll let you introduce yourself in whatever style you like best.
Yeah,
And
sure.
you can teach us a lot about blockchain security. And
Mm,
everyone, please keep your questions till the end. Just make a list, and then once he's done, he'll be able to answer all our questions. So great. I will just give you the co-host permission.
mm,
Done. You can share your screen.
all right, got it. Mm,
Let me know if there's anything else you need from my side.
mm, yeah, not it. I'm just figuring it out, like how I can share the complete screen. All right, I think
Perfect.
it's fine,
Oh,
right?
I can see lots of photos of myself.
Yes, it's just basically your channel.
Perfect.
Yeah. All right. Okay. Now, uh, let me know, sir. Like whether I can start or not.
Yeah, you can start.
All
Absolutely.
right. All
When you're
right.
ready.
Yep. So, hey everyone. Very good evening, according to the IST time zone, like where I live in, and very good morning, good night, according to your time zones as well. So, just a brief intro about me. My name is Tejaswa Rastogi, or better call me Razzor, because that's how people in the space know me with that name. So, yeah, basically, I am a smart contract auditor at Quill Audits. Quill Audits is basically auditing firm of Quill Hash, where we deal with all the security stuff on the smart contracts, blockchain, and typical projects like that. So yep, with that, I'm also a security researcher. I research about exploits, attack vectors, and different things, right? So if you want to connect with me, I'm available at LinkedIn, Twitter, with the name Razzor. Yep. Let me check if I can share some links. Mhm. Okay, where I can, okay, chat box. All right, right, cool. So with that, we're gonna start and we'll keep it very raw and we'll try to grasp every concept that I'm telling here in a very practical manner and like in a very layman's term for everyone to understand, whether you are a beginner or you are a very professional in the industry. Okay, so with that, I have written down some points that would help me to remember the things that I want to talk. All right, keep it aside. Okay, so the first thing that I want to talk is Web 2 versus Web 3. Now, we are very familiar with the Web 2 world, that how the Web 2 world works. Like there's a typical internet sort of architecture, or you can say server client technology, where the clients interact with servers. There are web applications on the server. So as a developer, you can deploy web apps on the server, and you can interact with them hosted on server, and you can interact as a client, right? So this is a typical Web 2 world where let's say an application is deployed and you found bugs later on, uh, it's, it's still possible for you to go on and make some fixes around those projects and still get a time margin to secure yourself, right? So that is one thing. But with Web3, there comes many features and there comes many, you can say, disadvantages, some sort of disadvantages. So we know the Web3 world is decentralized, right? So in Web3 world, uh, Web3 world is basically blockchain, right? Where the data is decentralized, where the database is decentralized, where everything is transparent, right? So let's talk about the basic and most fundamental feature of blockchain. The first thing is transparency, right? It provides transparency. Like there's no mediator between you and uh, your friend. Let's say your friend that you are interacting with, or let's say a project you are interacting with. There's no mediator. You can directly communicate or interact with the project itself. So that is the very major, you can say, advantage or transparency of that we got from this world of Web3 and from blockchain. And the second thing we got is immutability. So we know there are smart contracts. Smart contracts are, like, if I tell you in very general layman's term, smart contracts are just a piece of code that stays there on blockchain and runs on blockchain. Just a piece of code, or you can say an application that runs on blockchain, like things like that. So with that, blockchain says whatever code you want to deploy on the blockchain, that code will stay immutable, and nobody will be able to modify that code once it is deployed. So that is another cool feature of blockchain, because it creates a sense of trust. It creates a trustless environment onto the blockchain or onto the decentralized world, where no one has to trust any other third party. The only trust factor is the algorithms, the cryptography, the underlying technology, which is blockchain itself, right? So that is a very important and very important aspect of the blockchain, right? Now let's talk about this difference of Web 2 versus Web 3. Now we know, let's take a scenario. Let's take a Web 2 scenario. You have a web application that you want to deploy, and you deployed on your project. Now it's on the production. Now later on you found, okay, I missed certain bug in my project, and now that could like exploit the project, or that could cost me a fortune in terms of cost and things like that, right? So you got the exploit, you got the reason, like what is the actual problem in your code, and you can just go ahead and fix that issue. Yeah, that is completely fine. You're done. What about the Web3 world? Now imagine you deployed a smart contract, and later you found out, okay, I missed a very critical issue in my smart contract that could have been found in my internal testing, or when I was developing that code, right? So what you can do about it, like once your contract is deployed onto the blockchain, you can do nothing, right? It is there, it will just stay there forever. If it has any bug, it will be exploited by the attackers, and it will keep on getting exploited. There's no solution for you, right? There are certain ways which you can uh, tackle, which can use tackle with this implementation. So just give me a minute. I just got give me a just give me a second. Yeah, so sorry for that, sorry for the interruption. Yeah, all right, so I was talking about, yeah, like once you deployed your code or your contract onto the blockchain, now if you have not implemented any security feature, not security feature, any recovery feature in your smart contract to cope with all these future bugs, then you are done. There's no other solution that you can do. The attacker will keep on exploiting your code, and it will just stay there forever. So to reduce those risks, the very first step is to deploy a secure code, right? to reduce the number of bugs like as much as possible. There should be no major bugs in your code, right? That is something that you need to make sure, right? That's where the smart contract security comes into picture, and that's where the blockchain security comes into picture, right? So talking about blockchain security and smart contract security, they are kind of a correlated and kind of a different from each other as well, because blockchain security talks about the security of underlying technology itself, right? And smart contract security talks about the security of those web applications on uh, the code that we deploy on blockchain, the security of that, right? So these are two different things. So here, we'll talk about the smart contract security. Why smart contract security? Because uh, that's what gives the developer the independent power to make independent projects, right? There's no need, if you are knowledgeable enough, you know the language that being used on the blockchain, the respective blockchain, then you can just go and deploy your own project, right? So yeah, that is the thing. So this is why we need smart contract security is to make sure that there should not be any major bug in your code, and you reduce risk uh, from your code like as much as possible. So that is the most important thing. The next thing what I should cover, yeah, I covered this. Okay, now we can talk about the types of issues and bugs that may exist in the world of smart contract security, right? So there, you must have remembered, you must have listened, heard different attack vectors, different like if you follow Twitter, if you follow newsletters, like every day you found a completely new bug exploiting a project in a certain manner, right? So if we categorize the type of bugs, some types can be the first could be a logical bug, right? Or you can say incorrect implementation. So these kind of bugs are just generated by the developer itself, right? The reason is you have not implemented the logic of a function, let's say, or a contract itself in a correct manner, right? So that's where your project got a flaw and it got exploited, right? So this is the first thing. The second is the type of bugs that come from the language itself, like let's say compiler issues, right? So this is something that is not your fault basically, but it was a bug that it was there in the language itself, like which is if we pick Ethereum, the language is called as Solidity. So these are kind of bugs that were there in the language itself. So nothing much you can do about that. You can just wait for the team, the Solidity team, to fix those issues and patch those issues and move on to a newer update, and you can start using the latest version on latest update, right? So that's where it is being recommended that you should always pick up a latest compiler, right? Like not very latest. If we talk about Ethereum or Solidity, uh, if you talk about Solidity, so latest compiler major version is 0.8, right? 0.8, if I remember correctly, it's 0.8.11 or 10. Yeah, let's pick up 11. That's what I remembered last. Okay, so this is actually the latest compiler version in Solidity. Now it is being recommended that you should always use a somewhat latest version. Like you're not supposed to use the very latest version, like you want to be very sure and you will be just using 0.8.11 in your projects. Now that is also not recommended, because the reason is the very latest compilers can also have undiscovered bugs in themselves as well. So that's why it is not recommended to use the very latest of the compilers, but you should still be using the at least the major version. So you should still be going on with 0.8 compiler version. So like reducing the risk or reducing the number of bugs that were there in compiler versions prior to this, and minor versions greater than to this compiler versions, right? So this is the one. So for these issues, as I just told, it is nothing much that we can do. We can just wait for the Solidity research and development team to just work upon, fix those issues, and give us a patched version, right? The next one that we can categorize are generated because of the nature of the blockchain network. Right? Let's pick up Ethereum. So one attack vector or one exploit is called as front running. Right? Now, front running is a attack vector that is generated from the nature of the network or behavior of ecosystem. Right? So, like, why so? Because uh, I'll come to this part when we'll talk about this. So we'll talk about why they are attack vectors, because of the nature of the network, and we can't do much about that as well. We need to make sure that uh, if there are implementation in my contract that depends upon uh, those possibly flawed vectors, then we can reduce those vectors as well, right? But still, there are nothing much that we can do with that, because that's how the ecosystem is working, right? So that is one thing. Now let's talk about the flaws, and we'll try to gather information and try to understand some of the attack vector. So I have picked some of the most widely exploited and most popular attack vectors. And the first one is, obviously we know, is reentrancy. So you might have heard about this concept, this attack vectors. If not, no issues. I'll try to make you understand in a very uh, simpler manner. Okay, let's do that. So let's understand, like, what is actually this reentrancy. Reentrancy, all right. Oh, reentrancy. So it's like, if you are experienced with any programming language, let's say, let's pick up C or C++, Python, I guess. So there's a concept called as recursive functions. Recursive functions. So these are those kind of functions which call themselves. For example, let's say there is a function X, and because we want to reuse my code, right? Let's say it calculates factorial of a number. Factorial of a number. Now, just because we know how the factorial is calculated, we'll try and we'll try to reuse our code in such a way that for a number, it should repeat itself in a loop, right? We'll build a logic around that to calculate a factorial of a number, so that we need not to calculate the multiplication of each number respective time. We'll just say function X, and we'll try to repeat this process for, let's say, a number and -1 or things like that, right? So this is a very basic concept of recursive function. Now, in the same order, this reentrancy issue works. So let's say, let's take an example. Let's say you are a user A. You are a user A, and you are sending some money to your friend, user B. Now, user B has enough knowledge about development and all the attack vectors, and he or she know how to exploit reentrancy if they exist in a code. Now, user A has a contract where there's a transfer function where a user user A can transfer some money to a destination address, and yeah, destination address, and after that money after that this user A will update some balance, like whatever the balance is there, and it will update its balance. So let's say user A wants to like send 500 tokens of like say 500 funds to user B. So what a normal transaction will look like, that user A has sent 500 tokens to user B, and after that it has updated its balance and reduced the balance to reduced 500 from its balance, like a very simple transaction and approach. And how this user can exploit this functionality is because of this transfer of money. What actually happens if we pick Ethereum protocol? What actually happens in Ethereum? Basically, when you transfer some funds, you actually send the control to that user, the execution control to that user. So right now, you have sent 500 tokens to user B. Now user B has the control, and it can do any operation it wants on the caller's account, a caller's contract, a caller's code, right? Which user A never thought of, right? So user A thought, okay, I'm just sending 500 tokens, what user B can do, but having not enough knowledge of like reinsurance and all, user A thinks that is all safe and it will all work just fine. But what user B just got, user B got the control of this because of this transaction, and user B can again call the transfer function to again transfer funds to this user. And this will repeat the process on and on and on. Now, what is the problem with this thing is basically in Ethereum, the operations work step by step, right? So what was the transaction? Send money and update, right? So what is the problem? Like user B is in a loop exploiting this withdrawal feature, and it is in loop calling the send money and retrieving money from the contract. But what will happen? This update function can only this operation will only be executed after this call gets completed, this loop, right? So let's imagine it's in the loop of withdrawing money, user B in a loop withdrawing money again and again, but the update balance will only be updated by the last call, right? So what will happen? The user B is continuously retrieving 500 tokens again and again, and it will drain all the contracts balance or all the users balance, and the update will only reflect a deduction of 500 tokens, right? Instead of making it zero, it will just reflect the 500, deducting 500 tokens. So that is a very critical issue that is supposed to be removed from the code at the very early stage as possible. We'll see a demo. We'll see a demo of it to better understand this thing. Written down a very basic thing. So just do that. Okay. Deploy attacker as well. Now here I will be asking a question from you as well, you all. Okay, let me just deposit some balance in. Okay, so V is the very smallest, the smallest unit of the native cryptocurrency in Ethereum. So I'm depositing some balance into the contract so that the contract have some balance. Okay, now we'll transfer money. Uh, okay, now, okay, right. So the balance here in the contract, that's my liquidity. So in my contract, I have a balance like this much balance, right? And this is an attacker address, right? And like the user B that I talked about, having all the knowledge, like a very uh, malicious mind, right? So here, user A is trying to deposit to transfer, let's say 100 value. So now my question is, here I'm in a loop. Uh, so here, let me just give you a quick walkthrough of this code, this section. Basically, this is the same thing that I talked about. So whenever the contract or the user A will send money to this attacker address, this attacker contract. So this fallback function will be executed. This fallback function is the loop or the pathway where the attacker is making a loop. Because as I told you, in Ethereum, when an address sends money to or sends fund to another address, it actually gives control, execution control to that destination address. So here, after getting the control, what I'm trying to do, I'm again calling the same function, transfer money to my address. Address, this is my address, and with more value, with more funds. So I am in loop trying to retrieve as much funds as possible from the user A. So now my question is, I'm just trying to send 100, let's say 100 V to the attacker address. Now, what do you think? How much it will send and how much the attacker will receive? I'll give you like a quick minute to think about that. You can do your calculation if you want to. Okay, let's just do that. So user A basically did the transaction, send 100. The balance got updated with 49900, right? Earlier, it was, uh, right? Now it is, right? So basically, while transferring just 100 way, this user has lost this much amount of weight to this much amount of tokens to the attacker address, right? Now, if you check the balance, instead of receiving just 100, I received like 1 lakh 100 tokens, some sort of a value, right? This much high amount of value because I exploited reentrancy in this code, right? So now you must be wondering why 49900 this much value, because I am retrieving money in the chunks of 50,000. Let's just calculate this value. So earlier, I don't know if you can see this, if I can zoom it or, all right. All right. So earlier it was this much amount of value, right? Now, for the first time, I sent 100, right? 100 way to the user. Now it got as 14990. Now the attacker is has again called the transfer function and trying to retrieve 50,000. So what will happen? It will again remove 50,000, right? From this. Now the value comes down to a 99900. This loop will continue, and from this value will reduce more 50,000, right? So now it comes down to the value that we are seeing onto the screen, right? 49900. Now the loop stops here because I have given it a condition that if the target address balance goes down to this value less than 50,000, then you can break the loop and we are done. So now you have observed the reentrancy attack in practical. That's how reentrancy works. And this is the very, like I can say, the most critical exploit that exists in the Ethereum ecosystem. So that's why it is very important to observe this behavior and reduce this behavior. So the recommended behavior is to follow the check effects interaction pattern. Now, what is check effects interaction pattern? First, you need to check the required checks, like the restriction that you want to implement in your function. Then you are supposed to go with effects, like whatever state chain that you want to do, you should do that prior to any external call, right? So if you want to update the balance that we talked about here, the send money and balance update that was going on previously. So what is the recommended way is to switch this order. First, you're supposed to update your balance, then you're supposed to send money or make any external call. So with the same logic, if we have did this, so this reentrancy would have been prevented, right? Because firstly, what will happen here? What would have happened? Firstly, the balance would have been updated, and then the external call, which is sending money, have been made, right? So with this, for every call in a loop, firstly, the balance would have been updated and reduce the amount of funds. So with that, it would have actually stopped this attack vector to go go beyond a certain value, right? So this is actually the behavior that you should implement in your smart contracts. And there are other multiple scenario, you can go with reentrancy guards, which reentrancy guard is a very a famous helper library from Open Zeppelin. So you can implement reentrancy guard in your code, which will disallow any reentrant call in your smart contract. So if an attacker tries to exploit this feature and try to re-enter a call, it won't be possible, right? So the next one is another very popular thing is called overflows and underflows. So in Ethereum ecosystem, it exists in other languages as well. So it is like it's called as integer underflow or overflow. Integer overflow or underflow. So it is like every integer has a working space. Like if I talk about integer spaces in general, every integer has its own working space, like in which it can work and it can do operations or do calculations, right? Now let's pick up uint 256, right? So it gives you a space of 0 to 2 raised to 256 minus 1, right? This is the maximum feasible space that you can do operations in or calculations in. Now imagine you are giving a value -1 to this to a variable, right? Let's say there's a variable called x and you're giving a value as -1. This UN256 doesn't understand what is -1, right? Because there doesn't exist any negative numerals, right? So what it will do, instead of storing -1, it will wrap around space and move on to the highest possible value, right? And same goes for overflows as well. So this thing is called as underflow, because you are just a bucket, you are underflowing it and reducing the value to the like even less than the max, less than the least possible. And if you do, or if you give a value outside this upper bound, let's say a very high value, let's say 2 raised to 256 itself, right? If it doesn't come in this space, so what will happen, instead of storing that value, it will wrap around to the least possible value and make it 0. Now imagine scenarios where you are actually updating some state variables. Let's pick up the same example. You are updating balance after transferring some money, and you are updating the balance variable, right? Right. Let's say user had 500 tokens. It actually sent those 500. Not actually, it will not work in a theory system. But just imagine any calculation. Let's pick a very simple subtraction one. You are doing a 3 minus 2, which will correctly give you a 1. And if you do a reverse way, it will give you a very high value. We can also check this in practical. So this is a function which actually gives you the subtraction of two numbers. Let's say, like if I pick 3 and 2, it will give you 1, which is correct and the right behavior or right implementation. What if we give 2 and what if we give 3, right? So as we have discussed, it will result into -1, and -1 cannot be stored into a uint value. Uh, where it is with this function. Yeah, here. So we are subtracting two values and giving out the uint value. Uint is an unsigned integer, basically holds a positive value from 0 to 2 raised to 256 minus 1. So now here it cannot store a -1. So what it will do, it will just wrap around, right, to the highest possible value. So now imagine any scenarios where instead of this just simple subtraction, it is actually dealing with balance of funds. So now imagine a user accidentally subtracted or actually accidentally performed this kind of operation and got funds or tokens of value like this much. Now the user accounts this many of tokens, which is feasibly not possible, right? Yeah, a project can try to do that, but feasibly not possible. This is a very large value, right? So imagine a user got that much of funds, or a user can manipulate this according to it wish and get a value, a very large value, and drain out the complete contract or complete project itself, right? So this is another very well-known and major issue. And moving on to, let's talk about the thing that we discussed, uh, the nature, the thing that comes from the nature itself, from nature of network. So we know, pick up Ethereum as well for this. So we know that in Ethereum protocol, the transactions don't work like as first come first serve basis. So it's not like user A has sent a transaction, user B has sent a transaction after user A. This is first, this is sent second. So it is not like in Ethereum that Ethereum ecosystem will actually execute user A's transaction first as it came first, and then after it the user B's transaction. It is not like that. Actually, it depends upon the miners itself. Miners are for those who don't know about miners, miners are just there to create blocks to verify transactions, and they have the right to pick up the transactions, right? There are multiple factors that actually influence miners to decide the order of transaction that will be picked up first or the priority basis in the block that is going to be created next. And some of the factors are the major factor is the gas fees itself. With the EIP 1559, certain things are changed. But like to understand the scenario, let's keep the fact of minor fees or transaction cost. So transaction cost actually directly or the gas fee directly goes to the miner, right? So what miners actually do, they try to arrange these transactions in terms of highest gas cost, so as to get the maximum rewards possible as maximum rewards possible from a block, right? So if user B has given a gas cost, a user A has given a gas cost of let's say 10, and user B has given a gas cost of let's say 50. So user B's transaction will actually be picked up first, right? So imagine a scenario, let's say a scenario of a lottery system, right? There's a contract, uh, not lottery. Let's pick up a uh, yeah, lottery works as well. Sorry for that. Yeah, lottery works as well. Yeah. So there's a lottery system, but actually works upon a random number. So there's a contract X, and contract X will give this much amount of ethers, yeah, very high value, this much amount of ether to any address which will give the correct number, the correct random number, or the correct ask number. Like whoever firstly gives that will be considered as the winner, and all the funds will be given to the address as a way of incentive, as a way of reward, right? So imagine contract act user A actually got that number, and he or she is very desperate. Okay, now I'm going to win this much amount of like billions and billions of dollar, and it actually sends the correct number, let's say number Y. The correct number was Y, and made a transaction, and it goes into the Ethereum network, right? Ethereum network. Right, Ethereum network. It goes into the Ethereum network. Now, it has not yet executed. This transaction A, like A's transaction, is still there in the mempool or memory pool of the Ethereum network. And then because we know everything is public on the public blockchain, Ethereum is also public blockchain, everything is public, and any user can just come up and can see what are the pending transactions. User B came and saw this A's transaction and found out, okay, A transaction contains the right number, and A will be winning the rewards. So what user B will do, B will give the exact same number, but with a very high gas fees, in order to manipulate and convince the miner to pick up B's transaction first prior to the A's transaction. So actually, it was A who has found the right answer, but user B actually got the right rewards, or all the rewards from this transaction ordering kind of thing, right? So this is what it actually termed as transaction ordering, and popularly called as front run, because user B has actually front run user A in order to get rewards, right? So this is called as front running, right? So now you can understand you can't do much to protect front running in your project, but you are supposed to make sure you are not creating scenarios like that, which can result, which can allow users to create front running scenarios in order to uh, get rewards or any favorable stuff, right? So this is the thing. Now moving on to other attack vectors. Okay, so this is from the uh, world of Solidity, right? The high level language of Ethereum. Let's talk about the more popular DeFi attacks, right? Because DeFi is just a very a new crazy kid in the market, right? So DeFi attacks are also very popular, and there are lots of attack vectors, and you must have heard, you listen these about these hacks and exploits every day. So I'll try to cover very few of them. So the first one is called as unlimited ERC20 allowance, right? So ERC20, I guess everyone have heard about. Like ERC20 is just a standard of token on Ethereum, right? So ERC20 has it's just a standard of token. So ERC20 tokens have a feature where owner of a token can approve a spender with some value. So the concept is a owner can say, okay, hey spender, I'm giving you the permission to spend this much amount of tokens from me. You can spend value worth of tokens from my account. That is what I'm giving you permission to do so. Right. So like what is actually the use of this thing is, let's say, uh, not actually the use or the requirement. It's like you must have interacted with projects like where you are supposed to like stake some of your tokens, and you will be getting APIs rewards in return, right? So in order to do that, you are supposed to give permission to the project itself so that it can take your tokens from you, right? So that's where when this approve functionality comes into the picture. So the first thing you're supposed to do is to give uh, allowance to the project to spend to take out your tokens on your behalf in order to stake into the project, right? So this is the very basic functionality. Now let's take a very let's take a practical example of that, like how it actually happens. So I've created a workaround, not a workaround, a practical approach or a demo, you can say, exploit demo for this. So it is like, uh, yes, so yeah, the unlimited allowance. So basically, what actually happens, projects use this feature in order to rug pull users, in order to exploit users' funds. So it's like here you can say this is a lookalike of a malicious project. So first, let's say let's get some tokens. Let's get some tokens. Okay, let's get some tokens. Okay, let's get some tokens here. Right, so we can see okay, this is the one. All right, let me just find out. Okay, what I can do, I can just quickly go on. Right. Okay, no issues. All right, so I got some token. Let me try. Okay, I won't be able to. Yep, that's fine. So I have some tokens in my contract. These raise tokens, if I correctly check. Let's pick up another account to be 100% sure. Just remove any raise token. Okay, now let's get some tokens. All right, that is good. Now I should be getting some tokens here. Let's wait for transaction to finish. Let's try this one. Okay, let's see what happens. Okay, now I'm trying to just take one of my token, and let's just say what actually happens. Okay, I have to give permission. I'll approve it. Okay, I guess this is the one, the last one we had is the actual amount of tokens, right? So I'm trying to stake. I've given the allowance, and I'm trying to stake just one token. Right now you can see zero raise. So I just tried to stake one of my token, and the project or the contract actually taken or uh, uh, it has stolen all my funds which were there in my wallet, right? So this is actually kind of a scenario that is being generated because of unlimited ERC20 allowance. Because while approving or at the time of approving, I didn't check how many tokens I'm allowing this contract to take from me. And in the back end, like if I go on to this view for transaction details, if I go and edit, you can see this request, this approval request is actually taking this much amount of allowance of my tokens from me, right? I just want to stake one, but the project itself is taking an unlimited number of allowance from me, from my side, or from my wallet. So what it has now, it has all the permission to take out these funds from my wallet anytime possible. And the same thing was done by Unicast. Unicast was a very popular project, which actually rug pulled the users' funds twice because of this unlimited ERC20 allowance. And this actually happened recently as well. Uh, if I correctly remembered, which was there, I think Badger DAO was there. Badger DAO just faced the same exploit. Let me just check once. Yeah. So this was actually recently reported in the very famous exploit that just happened on the Badger DAO. So it was just same behavior where attackers actually injected some scripts into the front end and used their own control address to get the allowance of those tokens. So the intentional way was user A was actually giving allowance to the project or the contract code. But what attackers did, they injected a script where because of which the user was actually giving allowance to the attacker control address as well, right? So because of which attacker also has the permission to spend user's token, and that's when attacker has stolen like many users funds. This was uh, a very recent exploit in the DeFi that happened, and it because of the unlimited ERC20 allowance that I gave you a demo of. If you want, you can just go ahead and observe it yourself. I'm just giving you a link. Okay, where is chat box? Chat box. Okay, I hope you find it. All right, so this is the one thing. The other very cool exploit that not exploit, it's actually an intended behavior, but attackers use it to compromise applications and compromise projects. So you must have heard about this very famous and popular term, price oracle manipulation. Price oracle manipulation with flash loans, right? With flash loans. So flash loan is actually not an attack. Flash loan is an intended feature. So flash loan actually allows any user to take a liquidity or amount of tokens or kind of a loan, like any arbitrary number of tokens, whatever they want, a very high amount without any collateral, right? Without putting any collateral. You can take a loan of any amount of arbitrary tokens you want without paying a collateral. The only requirement is you are supposed to pay that loan with some fees in the same transaction. So that's where it actually works. So how attackers actually use this cool feature of flash loan in order to exploit DeFi projects and do some price oracle manipulation. Now, if we talk about exchanges, the decentralized exchanges, we know like if I pick up the very popular Uniswap, so Uniswap actually works with a formula x multiplied by y equal to k. So where x and y actually denotes the token reserves in the pool, and k defines a constant. So it actually tries to maintain a constant value for these reserves. So let's say, firstly, it was like you provided 5, x, you provided 5, y. So the constant became 25. Now some swaps happened, and it is like, so here right now, the ratio is 1 to 1. For 1x, you're getting 1 y. Now, actually, what happened? You deposited more x, you took out y, right? So the ratio has changed, right? So the y is less in the pool and the x is more. But still, it will try to maintain the constant, and it will try to make the reserve to point out to the same constant, right? So that's when it will try to make the reserve equal, and the ratio will become for 3 tokens, you just have 7x, right? Things like that. Let's understand. Let's thoroughly understand this with a curve. So this x and y actually defines a curve like this, right? So let's say at the time of providing liquidity, this was x, this was y, right? So what will happen? let's say you deposited some X and you are trying to get some Y. So by depositing X, you are trying to increase the value of X, right? You increase the value of X. Let's say, okay, sorry for that. X and Y. It will be much better. X, Y, right? Now let's say you are trying to deposit X. What will it will do? You are actually increasing the reserve of X, right? Let's say you have increased the reserve of X to dx, right? And now you have taken some Y tokens, right? So you've actually decreased the value of Y to dy, right? Right, things like that. Now you can see the values, the reserves has changed. Now the ratio has also changed, right? Because there are more tokens of X and less tokens of Y, the price of this Y tokens has now increased because the Y is in rarity, right? There are less tokens in the pool. So as less tokens there will be, as more or as higher the price of this Y token will become, right? You can also follow this with the same example. Let's say it will go on decreasing, right? It will, the value will keep on increasing, right? So now to take out Y tokens at this point, you are supposed to give a very high value of X, right? The reason is because now Y is very costly to purchase or to take up, right? So this is the thing. Now, what generally happens, let's pick up share scenario. Let's pick up a project which is kind of a vault, right? So where the same actually happened, with this popular popular one, mono X. Let's confirm that it was mono X or not. Yes, it was mono X. So recently, because of a similar exploit, mono X project or protocol was hacked, exploited. So let's see how it was done. So let's say there was a world which is actually giving you shares based on the valuation of a token, right? Based on the valuation of a token. A very simple logic. You're putting in one X token, right? Let's say the valuation of one X token, the one token is just one share. So you will be getting one share, right? So what actually attacker did, or what is actually price oracle manipulation, is like the same behavior. The attacker took the flash loan and increased the price of the token X, right? Took the flash loan from a pool, increasing the price of the token out, right? So there are two tokens, right, in a pool. There can be many. Let's pick up example of two tokens. So you are depositing in token in, so you will be decreasing the price of this token in, and you are increasing the price of token out. A simple logic. So what attacker did, it actually took a flash loan and increased the price of token out to a very large value, right? The problem was flaw in the contract itself. Basically is in the swap function. So the swap function was actually allowing a user to swap for the same token, right? So this token in and token out were same. So you basically can do a swap for the same token, which logically doesn't make any sense. So technically, what should have happened? if you are even if you are doing the same swap, the function or the logic should have been implemented in a way that it should have canceled out uh, each other's update. Let's say you're swapping for the same token. The token in price will decrease. The token out price will increase, right? So as these are the same tokens, they will cancel out each other's update. But the flaw in the swap function was token out, the balance of token out uh, was actually modifying the value of token in, right? So the latest value, instead of canceling it out, token out, the value of token out was considered as the current value of from the oracle or current price of the token. So what attacker did, attacker manipulated the swap and increased the value of mono token to a very large value, and after that get a share, because as now the valuation is much more than previously. Earlier it was just 1 to 1 because that was the valuation was. Now one token was is like can give you 500 shares because it the price is much higher. So what attacker did, after taking a flash zone, doing this swap, increasing the value of token X, take out 500 shares for the same value of just one token. This is just an example. Take out a very large value of shares, and after that, withdraw those shares for the equal amount of X and Y pairs, right? So imagine the intentional logic was you give me a one, and because of the valuation it's just one share, you are getting one share, and when you withdraw you will get the same half token X and half token Y, right? But as the shares, the value of the valuation of this token is much higher, you can actually take out higher shares, and you can withdraw them as well, and you can take out a much larger value of tokens. That what actually happened, and attacker did the same thing, uh, increase the value of mono token, get more shares, and after withdrawing those shares to get a larger value of token X and token Y. So this is a very classic example of flash loan and how flash loan attack works, right? So these are some of the attacks that are very popular and I wanted to discuss. Sandwich is also a very popular attack in DeFi. It happens because of front running and back running. Front running is what that we just discussed previously, where a user tries to front run another user in order to get some rewards. And back running is where a user actually tries to back run a user in order to get some rewards. So actually the same thing happens with here as well in Sandwich, where let's say there was a transaction in DeFi and a user saw the transaction. So let's say a user is actually trying to swap some tokens, token X, token Y, swap some token X to token Y. So what this transaction will actually do, as a user depositing token X, it will decrease the value of token X and increase the value of token Y. A malicious actor or attacker saw this transaction, and he or she know, okay, this user's transaction will actually increase the price of token Y. So what I will do, I will send this transaction prior to this transaction. I'll try to front run this transaction, and I will buy those tokens, right, in order to increase the value of Y. And after that, the user's transaction will be executed. And as the attacker has actually increased the price of token Y, the token X will be swapped for a much lesser amount of token Y, because attacker has just increased the price of token Y. And just after this transaction, attacker can back run this transaction to sell those tokens, right, in order to get some rewards from this sandwich attack. So it's like a sandwich, you can imagine, where attacker actually first front run, right? Then after users transactions got in place and executed, and then back run in order to get reward, right? So this is another very famous attack in sandwich in DeFi, and uh, this actually happens like every minute because attackers have actually set up bots. The main task of those bots is just to sit and monitor the transaction in the mempool and just make a sandwich out of that. If you want to study more about sandwich attack, you can go and check our research that we did over sandwich attack. We presented this in the last year DEF CON, and you can study about sandwich and how we can protect them using zero knowledge proofs, right? How we can prevent them with right. So I'm sending it here. I just saw this. Yes. You can study about sandwich attacks and how we can prevent this. Moving on, now we can come on to a part where, like, if you are a beginner and or even you are from the Web2 space and you want to jump into this Web3 space, you want to learn about blockchain, you want to learn about security, you want to learn about smart contract development, smart contract security, right? So how you can approach your learning. So the first things, I'll be sending a lot of links here. So just focus on your chat box. So the first thing first is to follow the well-known newsletters, which continuously work on to provide you about new attack vectors or postmortems about those attack vectors, where you can actually learn about different bugs and actually learn about security and how you can reduce risk around those security issues which just got exploited in the wild. So the very famous which do work every day and every week. So the very famous ones. The first one is that we just started. So it's called Hashing Bits. So Hashing Bits is our newsletter. We'll try to cover the new bugs, new attack vectors every week. So this is the first one that you can go around, right? This is the first one. The second one is from Securium. Securium also doing an amazing job in order to educate the community. This is the Securium one, right? The third one is from a very well-known security researcher, Peter. Peter actually, I think from Coinbase, if I can remember. So Peter writes his own blog, and it's called a blog thread. Blog thread Substack, I guess. Is it the one? Yeah, this is the one. So yep, this is again a very informative one newsletter that you should always follow and get yourself educated. So this is the first thing that you're supposed to learn about new issues and new attack vectors every day. The second thing is to be in communities, right? Be in communities that are there and there are many security researchers. You can communicate with them. You can learn about different stuff. You can do discussions with them. So communities are also very important. So one such community is our community actually, and we created this for the sole purpose to educate people. We created this 2.5 years back. The sole reason is to help newcomers to get information as much as possible. So this is blockchain pen testing server. Here you can find any possible information in the wild of blockchain space. Everything is organized, and if you're a beginner, you can start from blockchain for beginners from here, from this channel, and learn as much as you want. uh, you can search about it. I can give you an white link if I have. Okay. Hmm, okay, so this one is yep, you can use this one to join our community and learn from here. The other communities are Securium itself. Securium just launched a bootcamp, and it is actually done, but all the content is freely available for you to learn. If you want to learn about uh, all the content, basically the Ethereum stuff, the Solidity stuff, the bootcamp had covered all of the concepts. So you can just go around Securium. I'm just giving you the link of the channel. You can head over Securium playlist and you will find all the stuff here. It's all about like best practices, so what tools you should use, findings from audit reports, the bugs, the pitfalls, everything like that. So this is another thing. What else do we have? The current Immunify. You must have heard about the name. They are doing a pretty amazing job. Immunify has a bug bound. Immunify is a bug bounty platform where any independent researcher can just go out and bug hunt in projects and get some monetary rewards, right? So do check out Immunify as well. You can search Immunify and you will eventually find it out. Solidity Dev is also a very popular community on Discord, where you can discuss about particularly about Solidity and Solidity issues. Let me check if I can give you an invitation of this as well. Can I keep it permanent? Okay, I cannot. If I can. Okay, I can. Sorry. Yes, you can join Solidity Devs, right? The community is also very helpful, and you will find my like-minded people over there as well. So this is another thing. And yeah, what about an organized course, right? I would recommend a course from InfoSec. InfoSec has a pretty amazing course over blockchain security, talking about consensus exploits, technology exploits, exploits about network, things like that. So I'm dropping a link about that as well. You can just head over and learn from here. And yep, this is okay. This is the course. What else do we have? Yep, and the other important thing is to read postmortems, right? Postmortems are released by there are many independent researchers as well in the community. Well-known Mudit Gupta, he is amazing, and he constantly work and independently do researches on the exploits that happened in the past, uh, or the projects that have some serious issues as well, and educate the community. So Mudit is there, Samson is there. I'm just dropping the names. You can find out on Twitter. Mudit Gupta and Samson is very famous and well-known security researcher. And they also write the postmortems of bugs that they found. And then there are also postmortems which are released by Immunify. So Immunify also releases their own postmortem. You can find them on Medium, if I guess. Immunify postmortems. Okay, Immunify. Okay, sorry. Mm, yes, yeah. This is one of the postmortem. You can just go around and check other postmortems as well on the Medium page. So this is Immunify. You should also follow postmortems as well. And okay, now what else? As I just told you, follow industry leaders. Our well-known Razzor is there. He like educate people and community like every day. He's always there. Follow other industry leaders as well. Mudit follows Samson. And yeah, do your own research. Yeah, that is very important. But there are many people in this community who are always there to help you. What else we can do? There are some CTFs available for you to actually practice these kind of bugs and actually learn by solving and learn by observing how these issues and bugs work. So they are very popular ones. There's Ethernaut by OpenZeppelin. Uh, yes, this is one. You can practice it up here. Second is capture the ether. Yes, capture the ether. You can go here and practice that. What else? Yeah. Other one is damn vulnerable DeFi by Tinko. Tinko is a security researcher from OpenZeppelin. He actually created a CDF kind of a platform where you can actually practice about DeFi attacks. So that is also a very good one. The fourth one is Cypher Shastra, where I contribute challenges and try my best to educate community. So this is a platform where I'm contributing stuff. And if you have any challenges, you can always ping me out and I will host your challenge as well. It's completely open source. So this is the other one. What else do we have? Okay, so now we got insights about how we can get into the space, what we can learn, and where we can learn, things like that. Now, what about your career opportunities in this world of smart contract security, right? So there are multiple positions and multiple positions according to different roles and responsibilities. The first one is the engineering role. You can be a blockchain engineer, right, where your responsibility is to work on the underlying blockchain technology. You're supposed to find issues. You're supposed to work on tools and yeah, things like that. You can be a smart. Sorry for that. You can be a smart contract auditor, where your role and responsibility will be to analyze the code, to test the code, to find bugs, and yeah, and secure projects. Yeah. So this is another one. You can be a security researcher, where your role and responsibility would be to research and try to find uh, better and optimize security solutions for the existing technology. And if you want to, like, let's say, as I said, optimize any existing algorithm or things like that, you can do that. So that is what the role of security researcher, where you can work in. Other one is cryptanalyst, where you will be working on the underlying cryptography algorithms, and your task would be to uh, find and work on new and secure cryptography algorithms, like, as you know, some algorithms that are existent today are like vulnerable to quantum computing. So you are supposed to work and develop and new algorithms which are secured by quantum attacks. So things like that. So yeah, this is the career opportunity. I guess yes. That is enough from my side. I hope you guys have liked this session and hopefully have learned something new. Yes, so with that, I'm actually done. And if you want to connect with me, you can just go over to LinkedIn, Razzor. You can always connect with me if you get any doubt, if you get any question to ask. I will always be there. And you can connect with Quill Hash and Quill Audits if you have any uh, future project that you want to audit by us, by our services. You can approach us as well. Quill Audits, search Quill Audits, and you will find us. And yep, here we go. And right, yep. So with that, I'm actually done with my session, and I would like to ask Razzor to get back onto the screen.
Sure. So, do any of you have questions that you would like to ask?
Hi, there was a mention about front running and another form of running. I think so.
Back running.
Back running. Tejas, can you explain more about that, please?
Yeah, sure.
By the way, what can you guys see on the screen? I hope the screen sharing we've switched off, right? What are you guys able to see on the screen?
You see the blank Google page.
Google page.
Now I think you should be able to see.
Yeah, we can see you now.
You can see.
Was it switched off the whole entire time?
No.
Yeah.
Hi, just right now.
Given me a heart attack.
No, worry about that. Are you able to see him? Is Tejaswa on the screen?
Yes.
Yes, right.
Awesome. Okay.
Yes.
Please continue.
All right. Yes, sure. So yeah, with that, I will open my whiteboard one more time. Okay. So, okay. Yeah. So let's just talk about front running. Okay. In the context of Ethereum. Right. So as I mentioned previously, in the Ethereum ecosystem, it's not like you have, let's say there's a user A and user B. So it's not like as user A has sent a transaction first and user B has sent the transaction after user A, it will not be executed in the same order. Like it may not be executed in the same order because Ethereum ecosystem doesn't work like that. There's no software implementation which is actually monitoring the order of the transaction. So it's like the software is there and monitoring, okay, user A has actually initiated this transaction and I should actually execute user A's transaction first. So it is not like that. It is actually defined by a concept called as or by users called as miners, right? So miners are actually there to take this transaction and execute them according to their wish, right? So why their wish? Because they want to generate some rewards as well, right? So let's say user A, because we know every transaction has some gas cost as well. Gas cost is actually there to define what operation and how many operations this transaction can perform, right? So gas cost is kind of a limiting factor. So you are not supposed to do more operations than the amount of gas you're passing, right? So gas is something, a kind of a monetary value that you are saying, okay, I want to perform these operations. This is my gas cost and this should work fine. Now, miners are actually incentivized to make blocks on Ethereum, right? every blockchain. So in context of let's become Ethereum as well. So miners are actually incentivized to generate blocks, and for that they are supposed to pick up transaction and pack them up in a block, right? So miner, let's say there is a miner, and he or she saw these two transactions in the pending pool, right? It will not be executed immediately. It will stay there in the pending pool, mempool, sorry, in the mempool as pending transaction. So users A transaction is also there, B's transaction is also there. Now miner has the right to decide which transaction should go first, right? So what it will do, it will try to arrange all the transaction. There could be other transaction as well. All the transaction with gas cost, like highest gas cost possible, right? So how it will try to arrange these transactions, it will try to calculate, okay, A is actually giving me just 10 as a gas cost, and B is actually giving me 50 as a gas cost. So I will get more rewards from B's transaction. So I should arrange these transaction as like B's transaction, and then after A's transaction, or if there are more transaction, I will execute them after B's transaction, depending on how much rewards these transactions are giving, right? So with that, actually, A has initiated the transaction first, but miner has arranged this transaction in such a order that A's transaction is actually getting executed after B's transaction, right? So this is how the intentional scenario works in Ethereum ecosystem. But this can be used as a kind of attack weapon, because we know everything is public on the Ethereum blockchain. You are interacting with the project, you're interacting with a contract, you are sending some money, you are sending a value, everything is public. Everyone can see that. So that's when I given you an example of lottery. So lottery, there was a function like whoever give me a correct number, or let's say a random number that I generated, whoever give me a correct number, I will give all the funds to that user. Now user A actually found, and like with all the calculations that it has done, it actually found, okay, the number is let's say ABC. Let's say any number. ABC is the real answer of that question which the lottery contract is made up of, and actually send this transaction. It is not yet executed. It is there in the mempool. B found this transaction, okay, and B found from the transaction, B actually got the correct answer. B said, okay, A has actually found the right answer, which is ABC, and A is now going to win all the rewards. So what I will do, I will pass the same value. I will pass the same number ABC, but a very high value of gas cost, right? Now B's transaction is also there. Both of these transactions are not yet executed, but when the miner will see those transactions, miner will try to capitalize as much as possible on the rewards. What it will do, it will execute the B's transaction first, and B will be getting all the rewards, where A should be getting the rewards, right? So this is what front running actually works, and how we can how attackers exploit this behavior on the Ethereum ecosystem. Now, the same in the contrary, this is called as backrunning. Backrunning is where if there is a possible scenario where user B is able to generate rewards by just backrunning a legitimate transaction. For say, here the scenario was user B can get the benefit if its transaction gets executed prior to A. Now, if there may exist another scenario where it is more beneficial for user B to actually execute just after A's transaction. So that is what called as backrunning. And if we combine both of these, front running and backrunning, we have an interesting attack vector called a sandwich attack. Sandwich attack is very popular. I told you with that example of liquidity pools and how user can manipulate first the amount of token, the valuation of a token. After that, the legitimate transaction will go through, and just after that, the attacker will backrun the transaction in order to generate some rewards. So that is what the concept of sandwich attack. Hope it's clear now.
Does this also happen on newer blockchains like Solana, Cardano,
Uh,
Algorand, or only on Ethereum?
I've not yet checked the concept, how the network is behaving on the Solana.
Okay.
But yeah, EVM-based blockchains actually have this kind of scenario.
Okay. Does anyone else have any questions? Okay, thanks a ton. It was a lovely lecture. I am going
Yeah, thank you so much.
to put this up and I'll share the link with you. And all the links that you mentioned in the chat, I'll be posting them in the description below the video.
Yeah, for
Thanks
sure,
a ton.
for sure.
Thank you so much. Bye-bye.
Yeah, thank you so much
Have a
for
nice Sunday.
giving opportunity to talk with all the wonderful people. And yeah, let's see you around.
Bye-bye.
Bye bye.
Thank you, Razzor.